So now that we've done a regular ANOVA, we're now going to do a factorial ANOVA with two independent factors. Now this ANOVA has two factors with at least two levels each, and these levels are independent. So the factorial ANOVA with independent factors is kind of like the one-way ANOVA, except now, instead of having one independent variable, we're going to be working with two independent variables. So here is an example. Researchers want to test a new anti-anxiety medication. They measure the anxiety of 36 participants on different dosages of the medication, 0, 50, and 100 milligrams. Participants are also divided based on what school they are attending, either high school or college. So anxiety is measured rated on a scale of 1 to 10, where 10 is high and 1 is low. Use alpha 0.05 to conduct this factorial ANOVA. So we can do the 7 steps of hypothesis testing for this factorial ANOVA. See here, just looking at the table, we have two independent variables, right? We have dosage with 3 levels, 0, 50, and 100. And we have school with 2 levels. We have high school and college. So those are two independent variables, and that's why this is a factorial ANOVA. So we're going to start off with defining our null and alternative hypotheses. And we actually have 3 of them. We have one for school, one for dosage, and one for the interaction. So that looks pretty normal. We're going to assume all the school groups are equal, and we're going to test to see if they're different. We're going to assume all the dosage groups are equal, and we're going to test to see if they're different. And we're going to assume an interaction is absent and test to see if an interaction is present. So that's 3 hypotheses. That means we're going to calculate 3 F statistics. Next, we're going to state our alpha, which, as I said, is 0.05. It's pretty much always 0.05. Next, we're going to calculate the degrees of freedom. Now we're going to have 5 different degrees of freedom to calculate here. One for school, one for dosage, one for the interaction, one for the error, and one for total. And we're going to be using these equations right here. Pretty easy. For A, for school, it's just A minus 1, so that's 1. For dosage, for B, B minus 1, that's 2. And those are our 5 degrees of freedom. You can see that everything, A, B, the interaction, and error, adds up to total. So you can check your answers that way to make sure you did it right. Now next, we're going to state the decision rule. And we're actually going to have 3 decision rules because we have 3 hypotheses. Now, in order to look up these critical value, that's going to be as part of our decision rule, we're going to use degrees of freedom for the effect and degrees of freedom for the error. So for school, we'll use 1 and 30. For dosage, we'll use 2 and 30. And for the interaction, we'll use 2 and 30. So we're going to go to this big F table that we have, where we have between groups degrees of freedom on the top and within groups on the side. So we're going to look up our first critical value using 1 and 30. We get 4.17. So for that hypothesis, our critical value is going to be 4.17. Then we go back, we look up 2 and 30, we get 3.31. So we are going to have critical values of 3.32 for those 2 hypotheses. So our 3 decision rules are, for school, if F is greater than 4.17, we're going to reject. And for dosage and interaction, if those Fs are greater than 3.32, we're going to reject. So we get to test 3 different hypotheses here about 2 main effects and 1 interaction effect. So now we can calculate our test statistic. In order to do that, we need to fill out this table. We already have the degrees of freedom, so I'm just going to put that in there. That's easy. And now we need to find the sum of squares. So we need to find sum of squares for school, for dosage, for the interaction, for the error, and for the total. So let's start that with school. This is the equation for sum of squares, school. Now we already know most of this stuff. We know B, we know N. We can put that stuff in there. That's simple. So let's just move on. The top part of the first fraction is saying the sum of all A sums squared. So that's what this looks like. Our A variable has 2 levels. We have A1, which is high school students, and A2, which is college students. So we need to find the sums of both of those conditions and then square those. And that's what goes on top. So you see we have 93 squared plus 84 squared. On the bottom we have B times N because there are 3 B groups. N is 6 because there are 6 people in each condition. T is just the total sum, so that's 93 plus 84, which is 177. and capital N is 36 because that's our total number of participants. So solving for that, we find a sum of squares school of 2.25. Next, we're going to do sum of squares dosage, which is a lot like sum of squares school, except now the A and the B are switched around. So now we're going to split up the groups based on dosage. We have 0, 50, and 100. So we have three sums, 30, 53, and 94. So now those are squared and put on the top of the equation, and everything else is mostly the same. The t is still the same, the capital N is still the same, lowercase n is still the same, and A is 2 because we have two A groups. So we put that in there and we find a sum of squares dosage of 175.17. Now we need to find sum of squares for the interaction of school and dosage. Now luckily, when you look at this equation, you can see that the last three parts, we've already found those. So we can just put that in there. That's stuff we already did, we don't need to think about that. We just need to find the first part. So what we need to do is find the sum of each cell, each A at each B. So A1 at B1, A1 at B2, A1 at B3, A2 at B1, A2 at B2, and A2 at B3. So we find these 6 cell sums. And we're going to add those together and square them at the top of the fraction just like that. So if you work through and solve, you'll find that the sum of squares for the interaction is 17.16. So now I'm going to skip error and I'm going to do total, because total is pretty easy. Again, we already know t squared over n, so we just need to find the sum of all y squared. Now the sum of all y squared means we're going to take every value, square each one of those values, and then add them together. So down here, I square every single individual value, and I find a sum of y squares of 1081, of 1081. So I put that in the equation, and we find sum of squares total of 210.75. So now we go back to our table, and we can put in all of those sum of squares. Now notice that we're still missing error. But lucky for us, that's easy to find. Remember that everything has to add up to total. So we can just subtract what we have from total and find sum of squares error. We can take 210.75 minus sum of squares school, minus sum of squares dosage, minus sum of squares interaction, and we find the sum of squares error, which is 16.17. So next we need to find a few mean squares. Now that's pretty easy. Remember, mean squared is always sum of squares divided by degrees of freedom. So we can find the mean square for school, dosage, interaction, and the error. We're just dividing SS by DF. That's pretty easy. And now we need to find our 3 F statistics to test our 3 hypotheses. Now our F statistics are always going to be MS effect divided by MS error. So for example, we're going to take the mean squares for school and divide it by mean square for error. We can take the mean square for dosage and divide it by the mean square for error. And we're going to take the mean square for the interaction and divide it by the mean square for error. So we get our 3 F statistics, 4.16, 162.20, and 15.89. And now we're almost done. We can finally state our results. We're going to compare those F's to our critical values. Now for school, we're going to retain the null hypothesis because it's not greater than 4.17. But for dosage and the interaction, we're going to reject the null hypothesis because both of those F's are greater than 3.32. So what does that actually mean? What is our conclusion? We can conclude that high school students and college students did not have significantly different anxiety levels. There was a significant difference between the 3 different levels of dosage. An interaction effect was also present. And that is a factorial ANOVA with 2 independent factors.